Okay, so let's start with today's lab. In today's lab, we will talk about PCA and how it can be clubbed with other classifiers. So let me share the screen. Okay, so I believe you can see the screen. Can you see the screen? Okay. So I have uploaded the material on Classroom, but let's first discuss what we need to do and then we'll talk about the material. So if you can see the notebook file, this is the file we will be working on. Just a second. So this is the notebook file, and the first thing is usual imports that we do. NumPy library, Matplot library. So first is usual imports. Second. NumPy, Matplot, sklearn, pandas, maths, and random, and then the program. So in program, I have started with the example that we discussed in class. If you remember, we talked about data of two variables, x1 and x2. Let's call it x and y, and values are 1, 2, 3, 1, 2, 3. We said that the covariance between x and y is very high. Right? Both are almost same. And then what we do is first we remove mean from the data. There is x minus np mean, y minus np mean. And once the mean is removed, we make the data as club the two column and make it a data, usual panda data frame making. And then let's see how does it look in our data set. So first let's calculate the covariance. What is the covariance between these two? And as most of you already know that since they are co-varying, 1, 2, 3, x and y both are co-varying. So covariance has to be very high. And if you remember our calculation of covariance matrix was something like this. The blue line which I have selected here. Right? 1, 1, 1, 1. Our covariance calculation was 1, 1, 1, 1. And how do they look on the two-dimensional space? So let's plot that also. Let me first hide this. So they are arranged something like this. 3 points, 1, 1, 0, 0, and 1, 1. After removal of the mean. Then what we do is we find out the eigenvalues and eigenvectors of this data point. And if you remember, the eigenvalues that we have found in our example, classroom example, was 2 and 0. So here it turns out to be 2.0 and 5.6 raised to e raised to minus 34. So almost kind of zero value. And what we inferred from this was the covariance along the eigenvalue 2 is very high, and covariance along the second eigenvalue 5.6 is variance along the eigenvalue 2 is very high, and variance along the value 5.6 into e raised to minus 34 is very low. So data is direction of variance is this diagonal. So we want to find out axis which represents this diagonal, where we can see the observe maximum variance. And the principal components in class we have found some different value, if you remember, 1 1 and 1 minus 1 or something like this. So this is almost same value, but this is normalized to 1. Normalized to 1 it means that if you square this value and sum up, it will sum up to 1. There is 0.49 into 0.49 or something like this. Right, so this is also same value, but just normalized. The values are normalized to 1. Yeah, so this is the value we want to find. This is what the principal component analysis algorithm would do. Given the data points x and y, or any other data points for that matter, given the data points, it calculates covariance matrix and finds out principal components corresponding to eigenvalues. Are you with me so far? Any questions? Okay. So let us see what happens actually in the algorithm. So instead of this our classroom example, let's take a more concrete example. So let's generate some numbers randomly, and the values of x are copied into y. So y is n into x. So again they are co-varying. So covariance will be again high. So if you see again, the principal components and covariance will be same. But the data point, now the number of data points are larger, and the data will look something like this. So once you find out the eigenvalues, you make eigenvectors principal component and project your data along the axis of eigenvector. So what we do is, if you see the eigenvectors are, or the principal component which is eigenvector is minus 0.7, minus 0.7, and minus 0.7 plus 0.7 for this. So you tilt your data points, which are right now in diagonal form, tilt the data point along the principal axis, and then you will need only one principal axis where the eigenvalue is very high. In this example, 1.554 into e raised to minus 1. And remove the another eigenvalue, that is 7.75 into e raised to minus 32, along which the variance is very low. So for that, here what we do is we transform the data, that is called PCATR dot transform. So what we have done is, first we have trained the principal components to find out PCA principal component. So here we are looking for two principal components. PCA is equal to PCA, n component is equal to 2. So we are looking for two components. Then as usual, like all other scikit-learn functions, PCA dot fit. So it will learn the principal components from the data. And this is where we have printed the principal components and eigenvalues. Once the principal components and eigenvalues are found, we want to project our data on principal component axis. So that is called transform, PCA_TR dot transform. So data will be lined up along the principal axis. And for that we have created the data frame, and we again print that data frame. So let me uncomment this now. So if you print that data frame now, it will look something like this. So this orange line that you see on your plot is the data arranged along the principal axis. And if you see, this is rotation of the data. And what degree of rotation is required? How do you calculate this degree of rotation? That degree of rotation is calculated, or data is rotated by a degree of the transformation that you have learned in your PCA. So you transform the data to this, or convert the, once you know the principal axis, you know the difference between the original axis and principal axis, and calculate them. So this is what PCA transform will do, and line up the data along that axis. This visual thing or representation thing where you represent the data on principal axis. So this forms the remaining two part of the tutorial. That now this is done on some other random data points. So random seeds of 100 data with standard deviation 1 and standard deviation 2. So two data points. One has standard deviation of 1, second is standard deviation of 0.33. So this is way of generating a data randomly from normal distribution and assigning it to x and y axis. Again, mean removal and all that. But here, this example is used to give you an idea of rotational matrix. So when, as I said, this transformation is actually a rotation. So how do you calculate this rotation is shown here. So here there is one example of rotation with the degree of this one. The angle calculated as np.arctan 1 by n. So 1 by n rotation, or arc tangent of 1 by n rotation that we have calculated here to see that how rotation is done. But in our case, or in our example, rotation is along the principal axis. So we see the rotation angle between the actual axis and principal axis. I have added the description in the lab manual that you will see, and then we'll again discuss on that. So there was another part of discussion where you might have questions on why rotation or how rotation is calculated. Let me share that also. The manual is here. If you no, not here. Manual is here. Why can't I open it? Okay. I think it's creating some problem in opening here. Okay, now it's open. So if you see here, the more detailed description of this transformation is given, like if you want to rotate by 45 degree and so on. But this angle of rotation is actually your eigenvalues or the principal component values where you want to rotate. So these eigenvalues can be mapped to angle and you can rotate along that angle. Yeah, so this is first part, the basic PCA. And then on this same random data, that blue color data, this one, the diagram which is on your screen. So on this blue color data, we have again done the same process of finding out the principal components by calling the function of PCA component to PCA transform, PCA fit. And then we try to print the data points. Let me hide this for a while. Oops. Okay, it requires this. No, not yet. No, so what I was trying to do is, oops, what happened? Oh, did I not compile the previous part or? Okay, so this is what I was trying to show. So along this this blue data point, once we find out the principal components, eigenvalues 1 and 0.1, so it means that the spread of data along this eigenvalue 1, that is red line that you can see here. Let me zoom in. So in this data points, the spread is lower. Know that where is the red line and where is the green line, so that you know with eigenvalues. So 1.012, the first eigenvalue, and the vector corresponding to the first eigenvalue, that is, I believe, this 0.701 and 0.712. Along this vector, the variance is higher. And for second eigenvalue, 0.11, and corresponding eigenvector or the principal component, that is 0.712 and 0.701, the variance is lower. So variance is lower along this line, green line, and variance is higher along the red line or red principal component. Right? Has the data been a completely round shape or square shape, in that case your both eigenvalues would be almost equal. That also you can try yourself by generating the data. And then this again, this transformation to put the data along the principal axis. And then make this orange dots. These orange dots are transformed data points along the principal axis. And after transformation, again you can, this green and orange, this original your transformation angles can be shown by this. So this is basic principal component analysis. This is the first thing that you need to do today. Just look at the manual which I have shared in classroom here as PCA. Look at this and do the redo the code given there the way I have done. So that is first part of the today's discussion. Second part of today's discussion is using PCA as a dimensionality reduction technique and then combine it with some other classifiers. Usually we do this with support vector machine, but I think this time we have done the PCA earlier. So I have clubbed the principal component analysis with naive-based classifier. So I have kept the SVM in discussion so that in future, if you want to look at the examples, you can look at the example. But I have put the SVM thing in bracket. So dataset that we are using here is called Fetch Olivetti Faces. This face database available for face recognition application. So let's see what kind of data set is there. So there are all kind of faces in the data set, as you can see on your screen. And what we want to do is we want to reduce dimension of this face data set. Right now, if you just take image as an input, the dimension will be data.shape is 400, 4096. So there are 4096 dimensions. So we want to reduce the dimension, and this reduction we want to reduce it to up to 150 column, so that n component is 150. In our principal component analysis, n component will be 150. And once you do the processing, you can also see the mean data reshape. So that data will be on lower dimension space. And reshaped image, you can see the reshaped image like this. So this is the image with reduced number of dimensions. And it is not just removed some pixel, but it is by learning all other images and then choose the best pixel or best dimension to represent the image. So this is called mean image removal. And the shape of resulting image will be 150, 4096. So sorry, 4096 are example. And we have removed the dimension from 400 to 150. So that much the dimension are reduced. So that is same thing, same principal component steps that we did earlier. But the difference is here, difference is that we are looking at the image data set now. So same transform, and then we can use this PCA transform data to perform classification. So instead of doing classification on entire image, we are now doing classification on data output from principal component analysis. So same thing, rest of the things will be same as the things that we did in naive-based classifier. So divide the data into training set and testing set. Right? So we use some data for training, some for testing, and then we do naive-based classifier. So SQL here again the bracket support vector means you can do this for support vector machine also. Only thing you need to change is these 3 instructions. Here instead of Gaussian naive-based you can use support vector machine. So description is still on support vector machine, but we are using naive-based classifier. Right? And then import the image and all that, the regular steps that we do for data loading and learning. And then from the Gaussian naive-based we have learned predict and calculate precision and recall. Precision, recall, F1 and support. So this is the data output for that. And print the confusion matrix. So another part last part that we learn here today is to pipeline the machine learning models. So here we have said that first we apply PCA on data and create a reduced dimension data, and then we use that new data, PCA output data, to train naive-Bayes classifier. So there is a pipelining. So far we have done it through separate instructions, but you can club them into single instruction in pipeline like this. You can call pipeline, and in pipeline you can define the two functions. One is PCA function, decomposition function. Second is Gaussian naive-Bayes function. So it will do the things in sequence automatically. You don't need to write separate instruction, but still rest of the things remain same. So fit the model and make predictions and calculate precision and recall. Yeah, so this is the assignment for today. This is the exercise. There are 3 questions which might not be there in the original assignment. So I will